3 million light-years distant, a galaxy rotates with such velocity it ought to disintegrate. The Triangulum Galaxy, a stellar nursery of immense proportions, births suns 100 times more massive than our own. We shall observe blue giants, celestial behemoths that exhaust their nuclear fuel in a mere few million years. Prepare to explore pink nebulae where stars expire within cosmic shrouds, and to discover rogue black holes, cosmic predators roaming the spiral arms. The journey commences. The Triangulum Galaxy spins like a cosmic whirlwind, a phenomenon that should have resulted in its destruction billions of years ago. Night after night, astronomers, using their telescopes, focus on the Triangulum constellation, witnessing the impossible. This spiral galaxy, officially designated Messier 33, rotates at speeds defying all known principles of orbital mechanics. Its outer regions move with such speed that they should be flung into the void, much like water droplets ejected from a rapidly spinning wheel. And yet it persists, a testament to defiance. This galaxy spans 60,000 light-years, encompassing 40 billion stars, arranged in perfectly formed spiral arms. These arms trace elegant patterns across space in a celestial ballet. However, the physics governing this dance are inexplicable. Newtonian laws dictate that objects farther from a central point should move more slowly, mirroring the behavior of planets within our solar system. Mercury races around the Sun, while distant Neptune proceeds at a far slower pace. But Triangulum transcends these rules. Stars at the galaxy's periphery move at velocities comparable to those nearer the center. Some regions even exhibit acceleration with increasing distance. It is akin to observing a merry-go-round, where the outer horses gallop faster than those near the center. The centrifugal force should rip the galaxy asunder, scattering its stellar constituents across the cosmos like cosmic debris. The enigma intensifies upon measuring the galaxy's mass. All observable matter, every star and gas cloud detectable, accounts for only 10% of the gravitational force required to maintain this spinning behemoth's integrity. The remaining 90% originates from an unseen entity, something that neither interacts with light nor ordinary matter. We term it dark matter. This ethereal material, an unseen framework encompassing the galaxy, exerts a gravitational pull that prevents its spiral arms from dispersing. Dark matter surpasses the mass of all visible stars by a factor of 5. However, its presence is only discernible through its gravitational influence. It's akin to comprehending a dance solely by observing its shadows. The implications are profound. Should dark matter permeate the entire universe, then all observable entities, every star, planet, and galaxy, represent a minuscule portion of existence. We resemble inhabitants of an immense city, perceiving only the streetlights, oblivious to the colossal structures surrounding us. The Triangulum Galaxy has performed this incredible cosmic ballet for more than 10 billion years. Countless stellar generations have been born and extinguished, yet this enigma persists. Each complete rotation consumes 200 million years, a time frame within which countless civilizations could have flourished and vanished on worlds orbiting its 40 billion suns. And this rotating mystery is merely the prelude to our exploration. Deep within the spiral arms of the Triangulum Galaxy, a truly remarkable sight awaits us. Cosmic nurseries nestled there are birthing celestial behemoths. NGC 604, the galaxy's largest star-forming region, blazes with the power of 600,000 suns. This stellar maternity ward stretches over 1,000 light-years, a region 40 times larger than the Orion Nebula, adorning our night sky. Within this churning vortex of gas and dust, gravity molds stars of such immense size that they dwarf our sun, as mountains dwarf pebbles. The process starts in silence and darkness. Vast clouds of hydrogen gas, each possessing enough material to construct 1 million solar systems, drift through space at temperatures just above absolute zero. These molecular clouds are the raw ingredients of creation, invisible to our eyes, yet dense enough to obscure the light of stars behind them. Then, a trigger initiates the collapse. Perhaps a nearby supernova sends shockwaves pulsating through the cloud. Or it could be the collision of two gas clouds in a cosmic fender bender. Regardless of the cause, gravity asserts its crushing, inescapable influence. The cloud begins to contract, initially slowly, then accelerating as its own gravity intensifies. What started as a gentle drift becomes a rapid plunge toward the center. As the gas compresses, it heats, much like air within a bicycle pump. Temperatures soar from near absolute zero to thousands of degrees. The cloud fragments into smaller pockets, each destined to become a star. However, in NGC 604's dense core, some fragments accumulate so much material that they evolve into true giants. These stellar behemoths contain 50, 70, or even 100 times the mass of our Sun. They burn at temperatures exceeding 40,000 degrees Celsius, shining 50,000 times brighter than the star that warms our planet. Their surfaces radiate a brilliant blue-white light, so intensely hot that they ionize the surrounding gas, painting the nebula in vibrant electric pink and turquoise hues. The most massive stars in Triangulum exist on borrowed time. While our Sun will steadily burn for 10 billion years, these giants exhaust their nuclear fuel in a mere few million years. They are akin to cosmic Roman candles, burning brilliantly yet briefly before exploding in spectacular supernovas that can outshine entire galaxies. The irony is profound. The most massive stars, those appearing most powerful and enduring, are actually the most fragile. They consume their hydrogen fuel so rapidly that they scarcely have time to develop planetary systems before their demise. Any worlds forming around these giants would be sterilized by radiation long before life could emerge. Yet their deaths are not without meaning. When these giants explode, they forge heavy elements within their cores and disperse them throughout the galaxy. The calcium in our bones, the iron in our blood, and the oxygen we breathe, all were forged in the nuclear furnaces of dying stars. Yet, even these colossal stars are dwarfed by the shadowy hunters lurking between galactic spirals. Within the luminous spiral arms of Triangulum, unseen predators drift through the void, akin to cosmic sharks. These renegade black holes originated from the demise of the most massive stars. However, unlike their counterparts tethered within binary systems, these wanderers have been ejected from their stellar nurseries. The violent asymmetry of their formation, resulting from a star's core collapsing in an uneven supernova explosion, propelled them across space at velocities reaching thousands of kilometers per second. Now they traverse the galaxy in solitude, each a gravitational behemoth possessing the mass of dozens of suns, compressed into a sphere smaller than any terrestrial city. They remain utterly invisible, detectable only when they consume something in their path. For the most part, they glide through the near-perfect vacuum of interstellar space, as silent and lethal as submarines in the ocean's deepest trenches. The Triangulum Galaxy likely harbors millions of these stellar mass black holes, the ghostly remnants of ancient star formation eras. Some formed when the galaxy was young and deficient in metals, resulting in black holes with characteristics distinct from those born in the present day. Others are refugees from galactic mergers, cast into erratic orbits when their parent galaxies were sundered by tidal forces. When a rogue black hole encounters a star, the consequences can be catastrophic. The black hole's gravity generates tidal forces that stretch and compress the star, much like a cosmic stress ball. If the star strays too close, it crosses the event horizon and disappears forever, increasing the black hole's growing mass. But if it maintains a sufficient distance, the black hole strips away the star's outer layers in a process known as tidal disruption. These stellar cannibalization events generate some of the universe's most energetic phenomena. As the torn stellar matter spirals into the black hole, it forms an accretion disk that blazes with temperatures exceeding millions of degrees. The disk launches plasma jets at nearly the speed of light, producing beacons visible from billions of light years away. The most perilous rogues are the ones we cannot anticipate. Unlike active black holes surrounded by luminous accretion disks, a solitary wanderer emits no light signature. It is akin to spotting a black cat in a coal mine. The only forewarning would be gravitational lensing, the manner in which the black hole's gravity bends the light of background stars, acting like a cosmic magnifying glass. For any planetary system in the path of a rogue black hole, the encounter would be apocalyptic. The black hole would not need to directly impact a planet to destroy it. Its gravity would disrupt planetary orbits, potentially flinging worlds into interstellar space or causing them to collide with their parent stars. The tidal forces alone could trigger massive earthquakes and volcanic eruptions that would fundamentally alter entire worlds. The most unsettling aspect of these cosmic predators is their longevity. While stars expire and galaxies evolve, black holes endure virtually forever. They will still be traversing the cosmos long after the last star has faded and the universe has grown cold and dark. In the distant future, they may be the only active entities in a lifeless universe, occasionally encountering one another in the darkness and merging in collisions that shake the very fabric of space-time itself. Yet, the marvels of Triangulum are not solely cloaked in obscurity. Within the galaxy's stellar nurseries, celestial artisans craft luminous masterpieces. Interspersed across Triangulum's spiral arms, delicate pink veils mark the final exhalation of stars nearing their demise. These radiant clouds, termed planetary nebulae, bear no relation to planets. The appellation originated with 18th century astronomers, who, through their rudimentary telescopes, mistook them for distant worlds. In actuality, each nebula represents a stellar death shroud, the outer layers of a sun-like star expelled into space during its final moments. This process commences when a star depletes the nuclear fuel within its core. For billions of years, the star maintains a precarious equilibrium between the inward pull of gravity and the outward pressure of nuclear fusion. However, when this fuel is exhausted, gravity prevails. The core collapses and intensifies in heat, while the star's outer layers expand and cool, transforming the once stable star into a swollen red giant. As the red giant phase progresses, the star's stability diminishes. Thermal pulses deep within its core generate shock waves that ripple through the stellar atmosphere. These pulses eject the star's outer layers in a series of gentle puffs, akin to cosmic smoke rings expanding into the vastness of space. The expelled material forms a hollow shell encasing the dying star. Initially unseen in the frigid darkness, a transformation then occurs, creating the beauty we observe. The star's core, now revealed as a white dwarf, burns at temperatures exceeding 100,000 degrees. This stellar ember bathes the expanding shell in ultraviolet radiation of such intensity that it strips electrons from atoms in the surrounding gas. The ionized hydrogen glows red, while oxygen emits green and blue light. The outcome is a cosmic stained glass window, adorned with impossible hues. Each planetary nebula narrates a unique tale of stellar death. Some form perfect spheres, their gas expanding uniformly in all directions. Others create intricate designs, hourglass shapes, or butterfly wings, sculpted by magnetic fields and companion stars. The most intricate nebulae resemble cosmic blossoms, with delicate petals of glowing gas arranged in symmetrical patterns that rival any human artistic creation. The timescales involved are both immense and ephemeral. The dying star required billions of years to reach this juncture, steadily burning throughout much of the universe's history. But the planetary nebula phase endures for merely tens of thousands of years, a mere cosmic blink. The expanding shell gradually dissipates into the interstellar medium, enriching the galaxy with heavy elements forged in the star's core. These elements serve as the building blocks for subsequent generations of stars and planets. The carbon in our DNA, the nitrogen in our atmosphere, the phosphorus in our bones, all originated in the nuclear furnaces of dying stars and were disseminated through planetary nebulae. We are, quite literally, composed of star stuff, recycled cosmic material that once radiated within nebulae such as these. The white dwarf at the nebula's center will continue to shine for trillions of years, gradually cooling from incandescent white to red, then brown, and finally black. This serves as a preview of our own sun's destiny, destined to follow the same trajectory when it exhausts its fuel 5 billion years hence. Our sun will expand into a red giant, consuming the inner planets, and then shed its outer layers in a final, breathtaking cosmic display. However, while some stars depart with gentle grace, others meet their demise in a spectacular outburst, briefly eclipsing the luminosity of entire galaxies. Within Triangulum's most vigorously star-forming regions, blue supergiants blaze like celestial torches, hurtling towards their own destruction. These colossal stars embody a profound paradox of stellar evolution. They are the most massive, luminous, and visually stunning stars in the galaxy, yet possess the shortest lifespans. A blue supergiant expends its nuclear fuel with the unrestrained energy of a Formula One race car, converting 4 million tons of matter into energy each second. The nuclear furnace at its core reaches 50 million degrees Celsius, a temperature sufficient to fuse elements up to iron. Its surface temperature surpasses 40,000 degrees Celsius, almost 7 times hotter than our sun. This extreme heat imbues the star with its characteristic blue-white hue and grants it a brilliance equivalent to 100,000 suns. The stellar wind it generates is so potent that it removes material at a rate that would completely vaporize our sun within only a few million years. From the moment of their ignition, these giants exist on borrowed time. While our sun will radiate steadily for 10 billion years, a blue supergiant depletes its hydrogen fuel in a mere 3 to 5 million years, a stark contrast, akin to comparing a gentle sip of water to the forceful torrent of a fire hose, both sourced from the same reservoir, yet consumed at drastically different paces. The star's death throes commence in its core, where nuclear fusion has generated layers of progressively heavier elements. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, oxygen into silicon, and finally silicon into iron. Each fusion stage releases less energy than its predecessor, analogous to a fire gradually diminishing as it consumes increasingly damp wood. When the core begins producing iron, the star's fate is irrevocably sealed. Iron cannot fuse to liberate energy. Instead, it absorbs it. The nuclear furnace that has sustained the star for millions of years abruptly transforms into an energy sink. The core temperature plummets, and with it, the outward pressure that has counteracted the star's own gravity. The subsequent events unfold with astonishing speed, faster than a human heartbeat. The core collapses from the size of Earth to the size of a city in less than 1 second. The density becomes so extreme that protons and electrons are forced together to form neutrons. The imploding matter rebounds off this neutron core like a rubber ball, striking concrete, generating a shockwave that tears through the star's outer layers. The ensuing explosion can outshine an entire galaxy. In mere seconds, the supernova releases more energy than our sun will produce during its entire 10 billion-year existence. The blast wave expands at 30,000 kilometers per second, heating the surrounding gas to temperatures exceeding 1 billion degrees Celsius. The supernova enriches the galaxy with heavy elements forged within the star's core and during the explosion itself. Elements heavier than iron, including gold, platinum, and uranium, originate solely from these cataclysmic stellar deaths. The shockwave also initiates star formation in nearby gas clouds, providing the galaxy with the seeds for the next generation of stars. The remnant after the explosion depends on the star's initial mass. Stars between 8 and 25 times our sun's mass leave behind neutron stars, objects of such density that a teaspoon of neutron star material would weigh as much as Mount Everest. More massive stars collapse into black holes, regions of space-time where gravity is so intense that even light cannot escape. Yet the ultimate driving force behind these stellar explosions, and indeed the entire galaxy, originates from a source we cannot perceive. A cosmic architect, unseen and untouched, shapes the universe from the shadows, enveloping every star, every gas cloud, every luminous spiral arm within the Triangulum Galaxy is an immense framework constructed from a substance we cannot perceive. Dark matter. 85% of all matter in the universe consists of this enigmatic material. However, its interaction with ordinary matter is limited solely to gravity. It neither emits, absorbs, nor reflects light. Imagine attempting to chart an invisible city by observing pedestrian movements, deducing building locations from the patterns of foot traffic. This mirrors our efforts to understand dark matter. Initial hints of its existence arose from analyzing galaxy rotation curves. Astronomers, measuring stellar orbital speeds around galactic centers, encountered an anomaly. Based on the visible matter within a galaxy, stars at its periphery should orbit far slower than those nearer the center, mirroring planetary motion in our solar system. Observations, however, revealed a different reality. Stars throughout the galaxy maintain nearly uniform speeds, regardless of their distance from the center. This is analogous to a merry-go-round, where all horses gallop identically, whether on the inner or outer ring. The only explanation for this phenomenon is the presence of 5 times more mass within the galaxy than is directly observable. This unseen mass forms a roughly spherical halo encircling the galaxy, extending far beyond its visible stars. Computer simulations demonstrate that, absent this dark matter halo, the Triangulum Galaxy would have disintegrated billions of years ago. Its spiral arms would have unwound, its gas would have dispersed into intergalactic space, and star formation would have ceased. The dark matter halo acts as a cosmic gravitational net, binding the galaxy while remaining completely imperceptible. It represents the ultimate cosmic construction project, a scaffold built from exotic particles that interact with ordinary matter only gravitationally. But what precisely constitutes dark matter? Frankly, we do not know. It could consist of weakly interacting massive particles, hypothetical entities predicted by particle physics theories but yet to be detected. It could be axions, extraordinarily lightweight particles exhibiting minimal interaction. Or it could be something entirely unforeseen, a form of matter so alien that our current physics remains inadequate to describe it. The mystery deepens when considering dark matter's pivotal role in the universe's formation. In the early cosmos, minuscule fluctuations in dark matter density amplified under their own gravity, giving rise to the universe's first structures. These dark matter halos became the seeds around which galaxies coalesced, providing the gravitational wells necessary for ordinary matter to collapse and ignite the first stars. Without dark matter, the universe would be radically different. Galaxies would be smaller and less stable. Star formation would be less efficient. The cosmic web of filaments and voids connecting galaxies across billions of light-years would never have formed. We might inhabit a universe devoid of large-scale structure, merely isolated stars drifting through empty space. The quest for dark matter has become one of science's greatest investigations. Deep underground laboratories shield sensitive detectors from cosmic rays, awaiting the distinctive signature of a dark matter particle collision. Particle accelerators collide protons at near light speed, hoping to generate dark matter particles in high-energy collisions. Space telescopes scan the cosmos for the gravitational signatures of dark matter clumps. Yet, despite decades of research, dark matter remains elusive. It is ubiquitous and yet invisible, holding the universe together while remaining completely undetectable by our instruments. The Triangulum Galaxy is embedded in a dark matter ocean, traversing an invisible medium that dictates its fate. However, within this dark ocean, brilliant beacons of light herald the birth of new stars, with spectacular cosmic pyrotechnics. Vast cosmic cradles, ablaze with the light of millions of newborn stars, are the deepest reaches of star formation. The largest of these regions boasts the combined brilliance of 600,000 suns. A single such stellar nursery possesses sufficient energy to power our solar system for billions of years. From afar, it presents as a rosy luminescence against the dark canvas of space. However, a closer look reveals a tempestuous crucible of creation and destruction. This region extends across more than 1,000 light-years, exceeding the distance between our Sun and its nearest stellar neighbor. Within this immense expanse, gravity molds the raw materials of space-time into the next generation of stars. Imposing pillars of gas and dust, some stretching several light-years high, serve as stellar incubators where new suns ignite. These pillars, while breathtaking, are ephemeral. They are sculpted by the intense radiation and stellar winds emanating from nearby massive stars, cosmic sandblasters, eroding the gas columns while simultaneously triggering further star birth. This is a delicate interplay of creation and destruction. Each new star contributes to the forces that will ultimately dissipate the very cloud from which it emerged. The younger stars remain nestled within their natal cocoons, detectable only through infrared light penetrating the enshrouding dust. These stellar embryos are nourished by accretion disks of swirling matter, spiraling inward, growing hotter and brighter as they approach the star's surface. Some of these disks may be developing planetary systems, laying the foundation for future worlds. The most massive stars in these regions burn with such intensity that they ionize the surrounding gas, creating luminous plasma bubbles expanding like cosmic soap bubbles. These emission nebulae paint the star-forming regions in vibrant hues: red hydrogen, blue oxygen, and green doubly ionized oxygen, a palette that would inspire any artist. The energy output from these stellar nurseries is astounding. A single massive star can generate as much energy in 1 second as our sun produces in an entire year. When dozens or hundreds of these giants coalesce in a single region, they form stellar associations that can outshine entire galaxies. The radiation pressure from these young stars is so forceful that it can expel the remaining gas, effectively halting further star formation. But the influence of these stellar nurseries extends far beyond their visible boundaries. The heated gas they generate ascends above the galactic disk, creating fountains of enriched material that cascade back onto the galaxy. This galactic fountain transports heavy elements, forged in stellar cores, to regions where they can be incorporated into subsequent generations of stars and planets. The stellar winds from massive stars collide and interact, producing superbubbles of hot gas that can grow to hundreds of light years in diameter. These bubbles act as cosmic mixing bowls, stirring the interstellar medium and distributing heavy elements throughout the galaxy. When the most massive stars explode as supernovas, they inject even more energy into these bubbles, sometimes breaching the galactic disk completely. The life cycle of a star-forming region follows a predictable sequence. It commences with the gravitational collapse of a giant molecular cloud, triggered by some external perturbation. Star formation proceeds rapidly, with the most massive stars forming first. These giants quickly begin to disrupt their birthplace, carving cavities in the gas and ultimately dispersing the cloud entirely. The entire process spans only 10 to 20 million years, a fleeting moment in galactic time. Yet, during this cosmic instant, these stellar nurseries transform the galaxy, enriching it with heavy elements and structuring the interstellar medium into the intricate formations we observe today. Even as brilliant star-forming regions illuminate the Triangulum Galaxy, ancient stellar cities hold secrets from its distant past. Orbiting Triangulum Galaxy, like ancient sentinels, are stellar time capsules preserving the memory of the universe's youth. Globular clusters, spherical collections of hundreds of thousands to millions of stars bound by mutual gravity, are among the galaxy's oldest objects. These stellar cities formed when the universe was less than 1 billion years old, making them living fossils from the cosmic dawn. Each cluster narrates a story spanning nearly the entire history of the cosmos. The stars within each cluster are roughly the same age, born from a single primordial gas cloud in a single burst of star formation. Unlike present-day star-forming regions, these ancient stellar nurseries were almost entirely hydrogen and helium, the simplest elements forged in the Big Bang. Heavy elements such as carbon, oxygen, and iron were virtually absent, creating a generation of stars unlike those born today. This chemical purity makes globular cluster stars living laboratories for understanding stellar evolution. Without heavy elements complicating their nuclear fusion processes, these stars follow predictable evolutionary paths. The most massive stars have long since exploded as supernovas or evolved into white dwarfs, leaving behind populations of smaller, longer-lived stars that will shine for trillions of years. The Triangulum Galaxy hosts several dozen globular clusters, each containing clues about the galaxy's formation and early history. These clusters did not form in their current locations. When they were born, the galaxy was a chaotic, turbulent environment with gas clouds colliding and merging in a cosmic dance of destruction and creation. The clusters formed in the dense cores of these colliding clouds then survived the galaxy's violent youth to become the ancient relics we observe today. The distribution of globular clusters around the galaxy reveals the shape of its surrounding dark matter halo. Unlike the stars in the galactic disk, which follow circular orbits, globular clusters trace elongated elliptical paths far above and below the galactic plane. These orbits map out the three-dimensional structure of the galaxy's invisible dark matter scaffolding. Each cluster is a gravitational masterpiece, stars packed so densely that the night sky from a planet within would blaze with thousands of bright stars. Gravitational interactions between these stars create a complex dance where stellar encounters can fling stars outward or cause them to spiral inward toward the center. Over billions of years, this gravitational evolution has sculpted the clusters into the perfect spherical shapes we observe today. Globular cluster cores harbor some of the universe's most exotic objects. Neutron stars, the ultra-dense remnants of supernova explosions, can be found spinning rapidly as pulsars, lighthouse beacons sweeping the galaxy with beams of radiation. Some clusters may even contain intermediate mass black holes, objects too massive to form from single stellar collapse, yet too small to be the supermassive black holes found at galactic centers. But perhaps the most remarkable aspect of globular clusters is their role as cosmic chronometers. By studying the colors and brightness of stars within these clusters, astronomers precisely determine their ages. The oldest clusters in the Triangulum Galaxy are nearly 13 billion years old, formed when the universe was less than 1 billion years old. They are among the first generation of stellar systems to form after the Big Bang. These ancient stellar cities have witnessed the entire history of galaxy formation. They have seen the galaxy grow from a small, chaotic collection of gas clouds into the majestic spiral we observe today. They have survived countless close encounters with other clusters, the disruption of galactic mergers, and the gradual chemical enrichment of the galaxy through successive generations of star formation. As we peer into these globular clusters, we are looking back in time to an era when the universe was young and the first stellar civilizations were taking shape. The Triangulum Galaxy's structure, though seemingly static from our perspective, is far more dynamic than its ancient star clusters might initially suggest. Its spiral arms, rather than mere aesthetic features, function as cosmic highways, directing the flow of gas and stars across tens of thousands of light years. This seemingly permanent whirlpool thus is, in reality, an illusion stemming from the immense timescales involved. The spiral arms are actually compression waves traversing the galactic disk, analogous to traffic jams moving along a highway, despite individual vehicles, in this case stars, constantly entering and exiting. This phenomenon, known as spiral density wave theory, elegantly explains one of the galaxy's most perplexing characteristics. Were the spiral arms simply material structures rotating with the galaxy, they would have wound up completely after only a few rotations, obliterating the spiral pattern. However, their persistence is due to these pressure waves, regions where stellar and gaseous density surpasses the average. As material orbits the galaxy, it encounters these density waves, much like a car approaching a traffic jam. Gas clouds decelerate, compress, and accumulate within the spiral arms. This compression triggers star formation, illuminating the arms with brilliant young stars and luminous nebulae. The most massive stars, burning brightly but briefly, fade before significant displacement from their origins, contributing to the prominent blue light emitted by the spiral arms. This process creates a cosmic conveyor belt of star formation. Gas flows into the spiral arms from the interarm regions, compresses into dense clouds, forms stars, and then disperses as stellar winds and supernova explosions return the remaining gas to the interarm regions. This cycle repeats every few 100 million years as the galaxy rotates. These spiral arms also act as cosmic rivers, channeling gas from the galaxy's outer regions toward its center. This radial material flow helps to clarify how galaxies sustain star formation over billions of years. Without this inward gas transport, the central regions would rapidly exhaust their star-forming fuel. However, this spiral structure is not perfectly stable. Computer simulations demonstrate that spiral arms can intensify, weaken, divide, and merge over time. Triangulum Galaxy's present two-armed spiral configuration may be temporary, perhaps a consequence of a recent gravitational interaction with a neighboring galaxy or the passage of a massive gas cloud. The arms also delineate distinct galactic environments. The spaces between the spiral arms are comparatively tranquil, exhibiting lower star formation rates and fewer supernova explosions. These interarm regions might be more conducive to the development of complex life, sheltered from the intense radiation and stellar violence characterizing the spiral arms. The galaxy's magnetic field aligns with the spiral structure, forming invisible highways for charged particles. Cosmic rays, high-energy particles accelerated by supernova explosions, trace these magnetic field lines as they propagate through the galaxy. This generates a complex three-dimensional structure where the visible spiral arms constitute only one element of a significantly larger architectural framework. The spiral arms also impact the galaxy's chemical evolution. Star formation within the arms generates heavy elements, dispersed by stellar winds and supernova explosions. These elements blend with the interstellar medium and eventually reach the interarm regions, becoming incorporated into subsequent generations of stars. This results in a gradient of heavy element abundance, varying with both distance from the galactic center and position relative to the spiral arms. Recent observations indicate that the spiral arms may be even more dynamic than previously believed. Some regions display spur-like structures branching from the main arms, creating a more intricate pattern than a simple two-armed spiral. These features could be transient, caused by local instabilities within the galactic disk or the gravitational influence of massive star-forming regions. The study of spiral structure in the Triangulum Galaxy has implications extending far beyond our local galactic neighborhood. Understanding the formation and evolution of spiral arms aids in interpreting observations of distant galaxies and provides insights into the fundamental physics governing galactic dynamics. At the heart of this grand spiral design rests the galaxy's most enigmatic region, where the typical rules governing stellar behavior might not apply. The Triangulum Galaxy's center is a zone so densely packed with stars and veiled in dust that we are only beginning to grasp its true nature. This galactic core, or nucleus, comprises less than 1% of the galaxy's total volume, yet harbors a disproportionate share of its most unusual phenomena. Here, stars are clustered at densities thousands of times greater than in our solar neighborhood. The night sky from a planet within this region would be a dazzling spectacle of brilliant stars, many bright enough to cast shadows. Unlike the supermassive black holes lurking at the centers of larger galaxies, the Triangulum Galaxy's core seems to lack such a behemoth. This peculiarity distinguishes it from most spiral galaxies, the majority of which possess central black holes containing millions or billions of times the mass of our Sun. The absence of a supermassive black hole suggests that the Triangulum Galaxy may have followed a different evolutionary path than its larger counterparts. Instead of a central black hole, the core region contains a dense aggregation of older stars, many of them red giants and supergiants that have evolved beyond their main sequence lifespans. These stellar ancients dominate the infrared light emanating from the galactic center, producing a warm glow detectable even through the obscuring dust clouds surrounding the region. The dust itself narrates a tale of stellar death and rebirth. Much of it consists of heavy elements forged in the cores of dying stars and dispersed via supernova explosions and stellar winds. Silicon, carbon, and iron atoms, created in stellar furnaces, now drift as microscopic grains through the interstellar medium, absorbing and scattering starlight. This dust forms a cosmic fog, making the galactic center one of the most challenging regions to investigate. Visible light from the core stars is almost entirely absorbed, compelling astronomers to rely on infrared and radio observations capable of penetrating this dusty veil. Each new wavelength unveils different aspects of the core's structure and activity. Recent infrared surveys have uncovered an unexpected level of star formation activity in the central region. Despite the apparent absence of a supermassive black hole, the core exhibits signs of recent stellar births, with young hot stars interspersed throughout the older stellar population. This suggests that gas is still flowing inward, collapsing to form new stars, possibly triggered by spiral arm dynamics or past gravitational interactions. The core also contains several unusual stellar objects that may be products of this extreme environment. Close stellar encounters in the dense core can strip matter from one star and transfer it to another, generating exotic binary systems and stellar remnants. Some of these objects may be blue stragglers, stars that appear younger than their surroundings because they have been rejuvenated by mass transfer or stellar mergers. X-ray observations have revealed another layer of complexity in the galactic center. Hot gas at high temperatures generates a diffuse glow extending throughout the core region. This gas may be heated by shock waves from supernova explosions or by the collective stellar winds from the region's massive stars. The magnetic field in the galactic core is notably strong and complex, twisted into intricate patterns by the galaxy's rotation and the turbulent motions of the gas. These magnetic fields may play a critical role in directing gas flows and influencing star formation rates in the central region. Perhaps most captivatingly, the core shows evidence of past violent activity. Expanding shells of hot gas suggest that the region has experienced periods of heightened star formation and supernova activity in the past. These starbursts may have been initiated by gravitational interactions with other galaxies or by the infall of large gas clouds from the outer regions. Studying the Triangulum Galaxy's core offers a unique laboratory for understanding galactic evolution. Unlike the violent active cores of larger galaxies dominated by supermassive black holes, this calmer nucleus allows us to study the more subtle processes that shape galactic centers across cosmic time. As we continue to penetrate the cosmic dust with increasingly sophisticated instruments, the secrets of the galactic heart gradually unveil themselves. Each discovery unveils another piece of the cosmic puzzle, illuminating how galaxies form, evolve, and ultimately meet their demise in the universe's grand choreography. Within the Triangulum Galaxy's most energetic regions, stellar metropolises blaze, fueled by the combined light of millions of suns. These immense star clusters, some harboring over 1 million individual stars, radiate so intensely that their brilliance is perceptible from billions of light years away. The largest of these stellar cities, known as superclusters, concentrate more luminous mass within a few dozen light-years than our entire local galactic neighborhood does in 1,000 light-years. The most spectacular of these clusters arose from violent star formation bursts, ignited by galactic collisions or the passage of colossal gas clouds. Under optimal conditions, a single molecular cloud can collapse, giving birth not to a mere scattering of stars, but to an entire stellar civilization instantaneously. This gravitational collapse proceeds with such rapidity that millions of stars ignite within a few million years, producing a stellar fireworks display, eclipsing entire dwarf galaxies in brightness. These nascent stellar cities are dominated by the universe's most massive stars, blue and white supergiants, burning at temperatures exceeding 50,000 degrees Celsius. The combined radiation from these stellar behemoths generates such intense pressure that it can disperse entire star-forming regions, carving vast cavities within the interstellar medium. The energy output from a single massive cluster can surpass the luminosity of 100 million stars like our Sun. These clusters themselves are gravitational marvels, their stars orbiting their common center of mass in intricate patterns honed over millions of years. The most massive stars sink toward the center through gravitational interactions, while smaller stars are flung outward. This process, termed mass segregation, establishes a stellar hierarchy where the largest and brightest stars dominate the cluster core. However, these stellar cities are not immutable. The very massive stars that render them so luminous also determine their fate. Within a mere few million years, the most massive stars begin to explode as supernovas, augmenting the stellar winds already pressing against the cluster's boundaries. Each supernova explosion sends shockwaves reverberating through the cluster, potentially triggering new star formation, while simultaneously dispersing the gas that could fuel future stellar births. The most violent clusters experience what astronomers call a supernova chain reaction. One massive star explodes, compressing nearby gas clouds and triggering the formation of even more massive stars. These new giants rapidly consume their fuel and explode in turn, creating a cascade of stellar death that can illuminate the entire cluster for thousands of years. Some of these stellar cities are so massive that they approach the boundary between star clusters and dwarf galaxies. The largest contain sufficient material to form their own gravitational wells, trapping gas and dust that can fuel multiple generations of star formation. These objects blur the line between stellar associations and true galaxies, representing a transitional class of cosmic structures. The stellar winds from massive clusters generate superbubbles of hot gas that can expand to thousands of light-years in diameter. These bubbles function as cosmic laboratories, where the interstellar medium is heated, compressed, and enriched with heavy elements. The expanding shells of gas eventually breach the galactic disk, creating fountains of hot material that rain back down onto the galaxy. The light from these stellar cities is visible across immense distances, acting as beacons marking the universe's most active star-forming regions. When we observe distant galaxies, the bright knots of light we perceive are often massive star clusters similar to those in the Triangulum Galaxy, cosmic lighthouses guiding our comprehension of galactic evolution. Even the dazzling brilliance of stellar cities pales in comparison to the destructive power of the expanding voids left by ancient stellar explosions. Scattered throughout the Triangulum Galaxy are immense hollows in space, cosmic caverns sculpted by the violent demise of massive stars. These supernova remnants are the expanding shells of debris remaining after stars explode with the force of 10 billion hydrogen bombs, detonating every second for millions of years. The shock waves from these explosions traverse space at speeds exceeding 10,000 kilometers per second, sweeping up interstellar gas and dust like cosmic snowplows. The process begins with a catastrophic collapse when a massive star depletes its nuclear fuel. Its core implodes in less than 1 second, rebounding in an explosion that can outshine an entire galaxy. The shock wave from this explosion tears through the star's outer layers, heating them to temperatures exceeding 1 billion degrees and propelling them into space at a significant fraction of the speed of light. This expanding shell of stellar debris collides with the surrounding interstellar medium like a cosmic tsunami. The collision generates a double shock wave system, one shock moving outward into the interstellar gas and another moving inward through the ejected stellar material. The region between these shocks becomes an intense furnace where gas is heated to millions of degrees, creating a glowing bubble of plasma detectable across the electromagnetic spectrum. The supernova remnant grows larger and dimmer as it expands, eventually reaching diameters of hundreds of light years. During this evolution, the remnant functions as a cosmic particle accelerator, using magnetic fields and shock waves to accelerate particles to nearly the speed of light. These cosmic rays then propagate throughout the galaxy, disseminating energy and information about stellar explosions across vast distances. The morphologies of supernova remnants narrate tales of stellar violence and interstellar structure. Some form perfect spheres, expanding uniformly in all directions through a homogeneous medium. Others create complex filament structures that trace the magnetic field lines and density variations in the surrounding space. The most spectacular remnants form intricate lacework patterns of glowing gas, with delicate filaments and knots revealing the turbulent physics of shockwave propagation. These cosmic caverns have profound effects on their galactic environments. The hot gas they generate rises above the galactic disk, forming chimneys and fountains that transport heavy elements from the disk to the galactic halo. This process helps regulate the galaxy's chemical evolution, ensuring that elements forged in stellar cores are distributed throughout the galactic ecosystem. The energy injection from supernova remnants also influences star formation rates in nearby regions. The shock waves can trigger the collapse of molecular clouds, initiating new periods of stellar birth. However, these same explosions can also disrupt star-forming regions, heating the gas to temperatures too high for gravitational collapse. This creates a complex feedback loop where stellar death influences stellar birth across multiple generations. Some supernova remnants interact, creating superbubbles when multiple explosions occur in the same region. These enormous cavities can grow to thousands of light years in diameter, dominating the structure of the interstellar medium across vast regions. The largest superbubbles can completely penetrate the galactic disk, creating pathways for gas to flow between the disk and the halo. The study of supernova remnants provides crucial insights into stellar evolution, interstellar physics, and galactic dynamics. Each remnant serves as a natural laboratory where extreme conditions generate phenomena impossible to reproduce on Earth. Even the ferocious outbursts of supernovae are dwarfed by the celestial choreography of binary star systems hurtling toward their inevitable demise. Within the Andromeda Galaxy, millions of binary star systems engage in an elegant gravitational dance, culminating in cataclysmic events. More than half of all stars in this galaxy are born in pairs or clusters, locked in orbital embraces that can endure for billions of years. These cosmic couples pirouette around their shared center of mass, their gravitational attraction maintaining a precarious equilibrium. neither drawing too near nor drifting too far apart. Yet this celestial waltz is not everlasting. The passage of time, stellar evolution, and the relentless pull of gravity conspire to orchestrate endings more dramatic than any earthly tragedy. The most frequent outcome awaits systems where one star significantly outweighs its companion. The more massive star evolves more rapidly, depleting its nuclear fuel first and swelling into a red giant. As it expands, its outer layers reach a point where the companion star's gravity surpasses its own. Matter then begins to flow from the giant to its smaller partner, forming a luminous bridge of gas between the two stars. This mass transfer fundamentally alters both stars. The donor star sheds mass, potentially extending its lifespan by ridding itself of its outer layers. The recipient star, conversely, gains mass and increases dramatically in brightness. In some instances, the infalling material creates an accretion disk around the smaller star, heating to millions of degrees and generating a brilliant X-ray source. This mass transfer process is seldom smooth or consistent. The flow of matter can be erratic, triggering nova explosions when sufficient hydrogen accumulates on the surface of the receiving star. These novae can temporarily boost the system's brightness 10,000-fold, producing stellar fireworks visible across vast galactic distances. However, some binary systems are destined for even more spectacular conclusions. When both stars are massive enough to form neutron stars or black holes, the system enters a death spiral that can stretch over millions of years. The two compact objects orbit each other with accelerating speed, their orbital energy dissipated by gravitational waves rippling through the very fabric of space-time. As the orbit contracts, the two objects spiral inward, akin to water circling a drain. The final moments of this cosmic ballet unfold in mere seconds, with the neutron stars or black holes orbiting each other hundreds of times per second before their ultimate collision. The merger unleashes more energy and gravitational waves than all the visible stars in the observable universe combined. These kilonova explosions generate conditions so extreme that they forge heavy elements impossible to produce within typical stellar cores. Gold, platinum, and uranium are created in the intense heat and pressure of the merger, subsequently dispersed into the interstellar medium, where they may become incorporated into future generations of stars and planets. The gold in our jewelry, the platinum in our electronics, all may have originated from the violent merger of neutron stars billions of years ago. The Andromeda Galaxy harbors thousands of these binary systems at various evolutionary stages. Some are just beginning their dance, youthful pairs of stars that will orbit each other for billions of years. Others are nearing their final acts, with white dwarf stars gradually consuming their companions or neutron stars spiraling toward merger. The study of binary star evolution has unveiled that stellar death is far more intricate and violent than previously imagined. While single stars may end their lives quietly, fading into white dwarf obscurity, binary systems can experience multiple episodes of mass transfer, nova explosions, and ultimately, catastrophic mergers that reshape the surrounding galaxy. These cosmic partnerships also serve as natural laboratories for testing our understanding of stellar physics and gravitational dynamics. The precise timing of pulsar binary systems has enabled astronomers to indirectly detect gravitational waves, confirming one of Einstein's most audacious predictions decades before direct detection became feasible. However, these dramatic stellar deaths contribute to a magnificent cosmic artistry, forming some of the universe's most breathtaking structures. Across the Triangulum Galaxy, expiring stars produce masterpieces rivaling any human creation. These planetary nebulae are cosmic canvases where physics transforms into artistry. Each nebula displays a unique blend of colors, generated by different elements glowing at specific temperatures and densities. Hydrogen, the universe's most abundant element, produces a red glow, while oxygen creates ethereal blues and greens. Nitrogen contributes deep red hues, and sulfur adds yellows and oranges to this cosmic palette. But the true artistry resides in the nebula's structure. Shaped by forces as intricate as any master painter's technique, the dying star, at its core, does not simply shed its outer layers uniformly. Instead, magnetic fields, stellar rotation, and the presence of companion stars sculpt the expanding gas into complex patterns defying simple explanation. Some nebulae form perfect rings, like cosmic smoke rings expanding through space. Others create hourglass forms, with narrow waists and bulbous ends, hinting at the influence of equatorial disks around the central star. The most intricate nebulae resemble butterflies, flowers, or even human eyes, with symmetrical patterns that appear almost intentionally designed. The Helix Nebula, sometimes called the Eye of God, showcases the incredible precision of these cosmic sculptures. Its elaborate braided structure contains thousands of individual knots and filaments, each a narrative of gas compression and magnetic field interaction. The nebula's colors shift from deep red at the edges to brilliant blue-green at the center, creating a three-dimensional artwork spanning several light years. The creation of these colors involves quantum physics at its most fundamental level. When the central white dwarf star bombards the surrounding gas with ultraviolet radiation, it strips electrons from atoms, ionizing the gas and causing it to glow. Each element glows at specific wavelengths determined by the energy levels of its electrons. The result is a spectrum of colors serving as a fingerprint for the elements within the nebula. The intensity and distribution of these colors reveal the history of the dying star. Red regions indicate areas where the ultraviolet radiation is weaker, allowing hydrogen to remain partially neutral. Blue-green regions mark zones of intense ionization where oxygen atoms have been stripped of multiple electrons. The boundaries between differently colored regions trace the shock fronts and density variations within the expanding gas. Some nebulae change their appearance over human timescales, allowing astronomers to observe the cosmic artwork evolve in real time. The expansion of the gas shells creates moving patterns of light and shadow as different regions brighten and fade. Knots of denser gas can be seen streaming from the central star like cosmic fireworks, while cavities carved by stellar winds create hollow spheres within the larger nebula. The symmetry of many planetary nebulae suggests that binary star systems play a crucial role in their formation. A companion star orbiting the dying giant can create jets of gas that pierce the stellar envelope, creating the bipolar structures seen in many nebulae. The gravitational influence of the companion can also create spirals and rings as the gas is shaped by orbital dynamics. These cosmic artworks are temporary, lasting only tens of thousands of years before the expanding gas becomes too diffuse to glow brightly. But in that fleeting moment of cosmic time, they transform the ordinary death of a star into something transcendent, creating beauty from destruction and order from chaos. The study of planetary nebulae has revealed the incredible variety of stellar death. No two nebulae are precisely alike, each a unique expression of the physical processes governing stellar evolution. They serve as laboratories for understanding atomic physics, fluid dynamics, and electromagnetic fields under conditions unreproducible on Earth. These gentle stellar deaths, however, do not represent the sole mechanism by which stars release their outer layers into the cosmos. Certain stars embrace a more tumultuous trajectory, shedding their outer envelopes via ferocious stellar winds, akin to cosmic hurricanes. In the most vigorously star-forming regions of the Triangulum Galaxy, stellar behemoths quite literally dismantle themselves. Wolf-Rayet stars stand among the universe's most extreme entities, immense suns reduced to their nuclear-burning cores by their own stellar winds. These stellar gales rage at speeds exceeding 2,000 kilometers per second, expelling material equivalent to Earth's total mass annually. Their potency allows detection from thousands of light years away, generating expanding bubbles of superheated gas that dwarf entire solar systems. These stellar outliers commence their existence as the galaxy's most massive stars, giants containing 50 to 100 times our Sun's mass. Yet, this immense size proves their undoing. The nuclear fusion within their cores burns with such intensity that radiation pressure exerts incredible force against their outer layers. Eventually, this pressure surpasses the star's gravitational hold, propelling the outer atmosphere into space at hypersonic velocities. The stellar wind from a Wolf-Rayet star is no gentle zephyr. It is a hurricane of atomic particles. The mass loss rate can surpass 1/1,000,000th of a solar mass per year, meaning these stars shed the equivalent of our Sun's entire mass in a mere few million years. This expelled material carries away not only mass but also angular momentum, causing the star to spin faster as it contracts, much like a figure skater pulling in their arms. What remains after this stellar evisceration is a bare stellar core, fusing helium and heavier elements in a nuclear furnace, reaching temperatures of 100 million degrees. The surface temperature of these exposed cores can exceed 50,000 degrees, making them among the hottest stars known. They radiate a brilliant blue-white light that ionizes gas across vast distances, creating luminous nebulae visible even from outside our galaxy. The stellar winds from Wolf-Rayet stars do not expand uniformly. Instead, they forge complex structures shaped by the star's magnetic field. Some winds form spiral patterns as they interact with binary companions, while others create bipolar outflows, launching jets of material in opposing directions. The most spectacular Wolf-Rayet nebulae resemble celestial roses or butterflies, with delicate petals of incandescent gas arranged in exquisitely symmetrical patterns. These stellar winds convey heavy elements, forged in the star's core, into the interstellar medium. Carbon, oxygen, and nitrogen, products of nuclear fusion, are scattered across the galaxy, enriching the raw materials for future star formation. Some Wolf-Rayet stars produce such copious amounts of carbon that they create carbon dust, painting dark silhouettes against the luminous backdrop of star-forming regions. The interaction between Wolf-Rayet winds and the surrounding interstellar medium generates some of the galaxy's most energetic phenomena. When these high-velocity winds collide with nearby gas clouds, they create shock waves capable of triggering fresh episodes of star formation. These winds also carve extensive cavities in the interstellar medium, creating bubble-like structures that can expand to hundreds of light years in diameter. But the most dramatic facet of Wolf-Rayet evolution lies in its conclusion. Having shed their outer layers, these stars expose their cores to space, creating conditions that lead to some of the universe's most violent explosions. The absence of a massive hydrogen envelope means that when these stars ultimately explode as supernovae, they produce different explosion types than typical massive stars. Some Wolf-Rayet stars may produce hypernova explosions, events so energetic they can generate gamma-ray bursts that outshine entire galaxies. These explosions are considered the birthplaces of the most massive black holes and may be responsible for some of the universe's heaviest elements. The study of Wolf-Rayet stars enhances our comprehension of stellar evolution. These objects represent a fleeting yet crucial phase in the lives of the most massive stars, a period when stellar winds reshape both the star itself and its surrounding environment. Open star clusters serve as invaluable natural laboratories, enabling the study of extreme stellar physics and the intricate interplay of nuclear fusion, stellar winds, and magnetic fields. However, even these powerful stellar winds are dwarfed by the gradual disintegration awaiting the galaxy's more sedate stellar populations. Within the Triangulum Galaxy's spiral arms, numerous stellar neighborhoods are slowly dissolving, their constituent stars drifting apart like autumn leaves scattered by a gentle breeze. These open star clusters, loose associations of hundreds to thousands of stars originating from a single molecular cloud, represent the galaxy's most ephemeral communities. Unlike the ancient, tightly bound globular clusters orbiting the galaxy's halo, these younger stellar groups are held together by weak gravitational bonds that progressively weaken over time. They are, in essence, stellar families in the process of disintegration, each member ultimately destined for a solitary existence within the galaxy. This dissolution process begins almost immediately after cluster formation. The most massive stars, which gravitate toward the cluster's center through gravitational interactions, exhibit short lifespans. Their explosive supernova deaths remove mass from the cluster, sometimes even ejecting other stars entirely. Each stellar demise weakens the cluster's gravitational hold on its remaining members. Simultaneously, the galaxy itself actively works against these stellar communities. As the cluster orbits the galactic center, it encounters tidal forces emanating from the galaxy's gravitational field. These forces stretch the cluster, drawing stars from its outer edges, much like ocean tides erode a sandy beach. This process, while gradual, is relentless, steadily stripping away the cluster's least bound members over millions of years. The cluster's galactic journey also exposes it to gravitational perturbations from giant molecular clouds, spiral arms, and other stellar systems. Each encounter can scatter cluster members, sending them on new trajectories that may never reunite them with their stellar family. It resembles a cosmic game of billiards, where chance encounters dictate which stars remain together and which are flung into the galactic wilderness. The rate of cluster dissolution varies, depending on the cluster's initial mass, density, and galactic location. Clusters originating in the galaxy's dense central regions experience stronger tidal forces and more frequent interactions with other celestial objects. Those born in the outer regions might endure longer, but they too eventually succumb to the galaxy's disruptive forces. The Hyades cluster, one of the nearest open clusters to our solar system, exemplifies this dissolution. Its core still harbors dozens of stars sharing a common spatial trajectory, but its outer regions have been dispersed over the past few 100 million years, scattered throughout our local galactic neighborhood. Our own sun was once a member of the Hyades, but has now drifted too far from its siblings to be readily identified as a cluster member. The dissolution of open clusters significantly contributes to the galaxy's chemical evolution. Each cluster contains stars of similar ages and compositions, forged from the same primordial gas cloud. As these stars disperse throughout the galaxy, they carry with them the chemical signatures of their birthplaces. The heavy elements they produce through nuclear fusion and stellar winds become integrated into the broader galactic medium, resulting in the intricate chemical patterns we observe today. Some dissolved clusters leave behind trails of stars with similar motions and compositions, forming moving groups traceable across the galaxy. These stellar streams serve as fossil records of ancient cluster dissolution, allowing astronomers to reconstruct the history of stellar formation and dispersal across cosmic time. The study of cluster dissolution has revealed a far more dynamic galactic stellar population than previously imagined. Stars do not simply orbit the galactic center in isolation. Instead, they participate in complex flows and streams reflecting the galaxy's turbulent history. The Sun itself may have originated within an open cluster that dissolved billions of years ago, scattering its stellar siblings across the galaxy. Furthermore, the process of cluster dissolution influences the potential for life within the galaxy. Stars born in clusters experience different radiation environments and gravitational perturbations than those born in isolation. The dissolution process can transport stars to new galactic regions, potentially exposing any planetary systems to conditions unlike those present during their formation. Concealed beneath the spectacle of celestial bodies lies a pervasive, unseen ocean, a cosmic matrix interconnecting every star, every stellar cluster, and every galaxy throughout the universe. This invisible expanse, flowing between the stars, forms a complex web of matter and energy that unites even the farthest reaches of the Triangulum Galaxy. The interstellar medium is far from a void. This cosmic sea possesses approximately 1 atom per cubic centimeter, a density so rarefied that it would qualify as a perfect vacuum by earthly standards. However, across the galaxy's 60,000 light-year diameter, this tenuous substance accumulates to billions of solar masses of gas and dust, representing roughly 10% of the galaxy's total mass. This invisible ocean exists in diverse phases, each characterized by unique temperature, density, and dynamic behavior. The coldest zones are colossal molecular clouds, where temperatures barely surpass absolute zero, enabling hydrogen atoms to coalesce into molecules. These clouds, the galaxy's stellar nurseries, possess sufficient density to collapse under their own gravity, giving rise to new stars. Between these frigid clouds flows a warm medium of neutral hydrogen, heated by starlight and cosmic rays to temperatures of several thousand degrees. This substance permeates much of the galaxy's volume, forming a diffuse atmosphere enveloping the space between star systems. It resembles the air within a vast cosmic cathedral, imperceptible yet fundamental to the overall structure. The hottest phase of the interstellar medium attains temperatures exceeding 1 million degrees, a consequence of supernova explosions and stellar winds emanating from massive stars. This superheated plasma generates bubbles and cavities that can expand to hundreds of light-years in diameter, producing a frothy texture evocative of cosmic sea foam. The hot gas ascends above the galactic disk, forming fountains and chimneys that link the disk to the galaxy's extended halo. These distinct phases do not exist in isolation, but engage in constant interaction, exchanging mass and energy in an intricate thermodynamic ballet. Cold clouds can be heated by shock waves from supernovas, while hot gas can cool and condense to form new molecular clouds. This results in a dynamic ecosystem where the conditions for stellar formation are perpetually evolving. The interstellar medium also functions as the galaxy's circulatory system, transporting heavy elements forged within stellar cores throughout the galactic ecosystem. When massive stars detonate as supernovas, they release carbon, oxygen, silicon, and iron into the surrounding medium. These elements blend with the pre-existing gas, gradually enriching the galaxy's chemical makeup and furnishing the raw materials for rocky planets and life itself. Magnetic fields traverse this cosmic ocean, influencing gas flow on galactic scales. These magnetic fields can accelerate particles to nearly the speed of light, generating the cosmic rays that pervade the galaxy. They can also direct gas flow, creating filamentous structures that connect distant galactic regions. The interstellar medium is also saturated with radiation from stars, cosmic rays, and the cosmic microwave background. This radiation field supplies the energy that ionizes atoms, dissociates molecules, and drives the chemical reactions that create complex molecules in space. In the densest regions, this radiation can be absorbed and re-emitted by dust grains, resulting in a complex interplay between matter and energy. Dust grains, though constituting only about 1% of the interstellar medium's mass, play a vital role in its evolution. These microscopic particles, smaller than the wavelength of visible light, absorb starlight and re-emit it in the infrared. They also act as catalysts for chemical reactions, providing surfaces where hydrogen atoms can combine to form molecules. The motion of the interstellar medium follows the galaxy's rotation, but it is far from uniform. Gas flows from the outer regions toward the center, propelled by spiral arm dynamics and gravitational torques. This inward flow provides the fuel for ongoing star formation in the galaxy's central regions, while simultaneously mixing material from diverse galactic locations. The study of the interstellar medium has revealed that galaxies are not merely collections of stars, but complex ecosystems, where stars, gas, and dust engage in intricate interactions. The medium serves as both the raw material for star formation and the repository for stellar remnants, creating a cycle of renewal that has persisted for billions of years. This imperceptible cosmic ocean, however, is far from tranquil. Within its depths, particles propelled to astonishing velocities by the Triangulum Galaxy's most violent events surge relentlessly. Though unseen by our eyes, these streams of subatomic particles, brimming with immense energy, approach the ultimate cosmic speed limit. Cosmic rays are not rays at all, but individual atomic nuclei, primarily protons and heavier atomic cores, accelerated to near light speed by the galaxy's most tumultuous phenomena. These subatomic projectiles possess energies millions of times, exceeding any achieved in Earth-bound particle accelerators, establishing them as the most energetic particles known. The most powerful cosmic rays carry energy equivalent to a baseball hurled at 100 kilometers per hour, yet concentrated within a single atomic nucleus smaller than a proton. Upon striking Earth's atmosphere, these ultra-high energy particles generate showers of secondary particles, spanning kilometers and comprising billions of individual particle interactions. The acceleration of cosmic rays to such extraordinary energies necessitates cosmic particle accelerators far surpassing any human-made devices. Supernova shockwaves are the leading candidates, employing magnetic fields and plasma physics to accelerate particles via a process called diffusive shock acceleration. As particles traverse back and forth across the shock front, they gain energy with each crossing, eventually attaining speeds where relativistic effects become significant. The galaxy's most potent accelerators are the remnants of supernova explosions, expanding shells of incandescent gas capable of sustained acceleration for thousands of years. These cosmic engines can accelerate particles to energies exceeding 100 billion electron volts, creating a population of high-energy particles that permeates the galaxy like an invisible haze. However, Supernovas are not the sole source of cosmic rays. The galaxy's most massive stars generate powerful stellar winds capable of accelerating particles to high energies. The collision zones where these winds meet the interstellar medium produce shock waves that act as natural particle accelerators. Even the galaxy's central regions, despite lacking a supermassive black hole, may contain acceleration sites where magnetic field interactions can boost particle energies. The highest energy cosmic rays, those with energies surpassing 100 billion electron volts, present a particular enigma. These particles possess such immense energy that they should interact with the cosmic microwave background radiation, losing energy through a process called the GZK cutoff. This implies a travel limit of approximately 50 million light-years before energy depletion, suggesting their origin within our local group of galaxies. Cosmic rays do not travel in straight lines through the galaxy. Instead, they trace intricate paths dictated by the galaxy's magnetic field, acting as an invisible labyrinth for charged particles. The magnetic field can trap cosmic rays, causing them to rebound across the galaxy for millions of years before escaping into intergalactic space. This magnetic confinement significantly impacts galactic evolution. Cosmic rays exert pressure, influencing the dynamics of the interstellar medium, potentially affecting star formation rates and the structure of molecular clouds. They also contribute to interstellar gas heating, helping maintain the warm phase of the interstellar medium that fills much of the galaxy's volume. The study of cosmic rays reveals a far more dynamic and energetic galaxy than suggested by visible light observations. These high-energy particles convey information about the galaxy's most violent events, serving as messengers from regions where normal matter is heated to billions of degrees, and magnetic fields attain strengths trillions of times greater than Earth's magnetic field. When cosmic rays interact with the interstellar medium, they produce secondary particles, including gamma rays, neutrinos, and antimatter. These secondary particles are detectable by space-based observatories, providing insights into cosmic ray interactions throughout the galaxy. The distribution of gamma rays across the celestial sphere reveals the locations of cosmic ray acceleration sites and the structure of the galactic magnetic field. Some cosmic rays might even contribute to the evolution of life. The high-energy particles, constantly bombarding planetary atmospheres, can trigger chemical reactions, forming complex organic molecules. They may also contribute to genetic mutations driving biological evolution, although excessive cosmic ray exposure can be detrimental to life. The cosmic ray population in the Triangulum Galaxy constitutes a considerable energy reservoir, possessing energy comparable to the galaxy's total starlight. This invisible component of the galactic ecosystem influences star formation, heats the interstellar medium, and may even affect the evolution of life on worlds throughout the galaxy. Even these high-energy particles, however, adhere to unseen pathways forged by the galaxy's magnetic architecture. Within each cubic centimeter of the Triangulum Galaxy exists an invisible framework, a scaffolding of magnetic fields shaping the cosmos on the grandest scales. The galaxy's magnetic field is approximately 1 million times weaker than Earth's, so subtle it would barely perturb a compass needle. Yet this tenuous field stretches across tens of thousands of light-years, forming a vast electromagnetic structure influencing everything from stellar genesis to the movement of cosmic rays. It resembles a cosmic nervous system, an unseen network connecting distant galactic regions through electromagnetic forces. This magnetic architecture mirrors the galaxy's spiral structure, its field lines tracing elegant curves across the galactic disk. The magnetic field's intensity is greatest within the spiral arms, amplified by the compression of gas in those regions. Conversely, it weakens in the inter-arm spaces, creating a complex three-dimensional pattern that reflects the galaxy's visible structure. These magnetic field lines function as invisible highways for charged particles, directing the flow of cosmic rays and hot plasma throughout the galaxy. Electrically charged particles become trapped along these field lines, spiraling around them in helical trajectories that can extend for thousands of light years, filling the galaxy like an invisible atmosphere. The origin of galactic magnetic fields remains a significant enigma in astrophysics. Some theories posit their presence from the galaxy's inception, remnants of primordial magnetic fields from the early universe. Others propose their generation through dynamo processes, where the galaxy's rotation amplifies weak seed fields over billions of years. The galactic dynamo functions like a cosmic generator, utilizing the galaxy's differential rotation to twist and amplify magnetic field lines. As the galaxy rotates, regions closer to the center move faster than those at the periphery, stretching the magnetic field lines and increasing their strength. This process can amplify initially weak fields by factors of millions or billions over the galaxy's lifespan. The magnetic field also plays a crucial role in star formation, acting as both a facilitator and an inhibitor of stellar birth. In molecular clouds, magnetic fields can support the gas against gravitational collapse, preventing star formation until the field is weakened or superseded by other forces. However, magnetic fields can also channel the flow of gas, creating filament structures that serve as pathways for material accumulating in star-forming regions. When stars do form, their births can disrupt the local magnetic field configuration. The powerful stellar winds from massive stars can entrain magnetic field lines, creating complex magnetic structures around young stellar objects. These magnetic fields can focus stellar winds into jets, producing the striking bipolar nebulae observed around some young stars. The magnetic field also influences the galaxy's chemical evolution. Supernova explosions can generate magnetic bubbles that trap heavy elements, preventing their mixing with the broader interstellar medium. The magnetic field can also accelerate particles to high energies, creating cosmic rays that transmit information about stellar explosions across vast distances. Recent observations of the Triangulum Galaxy's magnetic field reveal non-uniformity, exhibiting complex structures including magnetic spirals, loops, and reversals. Some regions show evidence of magnetic field lines twisted into helical configurations, possibly by the galaxy's rotation or the influence of neighboring galaxies. The interplay between the magnetic field and the interstellar medium generates a rich array of plasma physics phenomena. Magnetic reconnection events can release enormous amounts of energy, heating gas to millions of degrees and accelerating particles to high energies. These processes may influence the interstellar medium structure and the acceleration of cosmic rays. The magnetic field also extends beyond the visible galaxy, creating a magnetosphere that may protect the galaxy from intergalactic cosmic rays and other forms of high-energy radiation. This magnetic shield may be vital for maintaining the galaxy's star-forming capacity and supporting life across cosmic timescales. The study of galactic magnetic fields has shown that galaxies are not merely gravitational systems, but complex magnetohydrodynamic structures where magnetic forces play crucial roles in their evolution. The invisible magnetic architecture of the Triangulum Galaxy represents a fundamental component of its structure, as significant as the visible stars and gas in determining the galaxy's destiny. This elegant magnetic structure, however, resides within a far larger enigma that challenges our comprehension of gravity itself. The Triangulum Galaxy executes an impossible celestial ballet, one that contravenes the fundamental laws of physics as we currently understand them. When astronomers measure the orbital velocities of stars around the galactic center, they uncover a phenomenon that should not exist. According to Newton's laws of gravitation, stars situated farther from the center should exhibit slower orbital speeds than those closer to it. Consider our solar system. Mercury hurtles around the Sun at 47 kilometers per second, while distant Neptune proceeds at a mere 5 kilometers per second. This represents the natural order within gravitational systems. Yet, the Triangulum Galaxy defies these principles. Stars throughout the galaxy's disk maintain a remarkably consistent speed, approximately 100 kilometers per second, irrespective of their distance from the galactic center. Some regions even display stars accelerating as their distance from the center increases, as if the galaxy's gravitational influence somehow intensifies with distance. Imagine horses on a carousel. Those on the outer edge gallop faster than those nearer the center. This flat rotation curve, as astronomers term it, constitutes one of the most profound puzzles in modern astrophysics. If we sum the visible matter in the galaxy, every star and gas cloud we can detect, we obtain only about 10% of the mass required to account for the observed rotation speeds. The remaining 90% is unaccounted for, concealed within some form of matter that does not interact with light. The implications are breathtaking. If the rotation curve is accurate, then everything visible in the galaxy, every radiant star and luminous nebula, represents merely the tip of a colossal iceberg. The majority of the galaxy's mass remains invisible, detectable solely through its gravitational effects on visible matter. Three potential explanations exist for this cosmic mystery. First, our understanding of gravity might be fundamentally flawed. Newton's and Einstein's theories could break down at galactic scales. Some physicists have proposed modified theories of gravity that could explain these rotation curves without postulating invisible matter. However, these theories struggle to reconcile other observations. Second, the galaxy might contain vast quantities of ordinary matter that we are presently unable to detect. This could encompass brown dwarfs, black holes, or dense molecular clouds too cold to emit detectable light, but comprehensive searches have failed to uncover sufficient quantities of these objects to explain the missing mass. Third, the galaxy might be embedded within a halo of exotic matter that interacts only through gravitational forces. This dark matter, as it is known, would surpass all visible matter in the galaxy by a factor of 5 to 1. Computer simulations indicate that such a dark matter halo could account for not only the rotation curve, but also the galaxy's stability over billions of years. The rotation curve also unveils the three-dimensional structure of the galaxy's mass distribution. The curve's flatness extending to the galaxy's visible edge suggests that the dark matter halo extends far beyond the visible stars, potentially encompassing a volume hundreds of times larger than the luminous galaxy. We might be observing only the bright core of a far more extensive invisible structure. This dark matter halo would contain approximately 100 billion times the mass of our Sun, making it the dominant component of the galaxy's gravitational field. The visible stars and gas that constitute the galaxy's exquisite spiral structure would be mere passengers, borne along by the gravity of this invisible ocean of exotic matter. The study of rotation curves in thousands of galaxies has revealed that this phenomenon is universal. Every spiral galaxy exhibits the same pattern, with rotation speeds remaining roughly constant or even increasing with distance from the center. This implies that dark matter is not a peculiarity of our local cosmic neighborhood, but a fundamental constituent of the universe. The Triangulum Galaxy's rotation curve continues to challenge our understanding of cosmology and particle physics. It suggests that the universe is far stranger and more intricate than we previously imagined, dominated by forms of matter and energy that remain profoundly enigmatic despite decades of intensive research. As we delve deeper into the galaxy structure, we encounter phenomena that push the limits of known physics and hint at cosmic forces beyond our current comprehension. The rotation curve serves as merely the initial step on a voyage into the unknown, a realm where the familiar laws of nature might not hold sway. Hidden within the Triangulum Galaxy's stellar populations are ancient witnesses to cosmic upheavals that shaped its violent past. Each generation of stars bears the chemical fingerprints of its birthplace, forming a stellar archaeology that unveils the galaxy's tumultuous history. The oldest stars, formed when the universe was young and pristine, contain almost no heavy elements. They consist of nearly pure hydrogen and helium, the only elements created in the Big Bang's nuclear furnace. These ancient stellar fossils narrate a tale of galactic cannibalism and merger-induced violence. When astronomers analyze their chemical makeup, they discover evidence that the Triangulum Galaxy has consumed smaller galactic companions throughout its existence. Each merger event left its mark on the stellar populations, creating streams of stars exhibiting unusual chemical abundances and orbital trajectories. The galaxy's stellar halo displays the most dramatic evidence of this violent history. Unlike the orderly rotation of disk stars, halo stars follow chaotic orbits that carry them far above and below the galactic plane. These stellar refugees are survivors of galactic collisions, torn from their original homes and scattered to the galaxy's outer regions. Some halo stars move in retrograde orbits, traveling in the direction opposite to the galaxy's rotation. This counter-rotation is the definitive proof of galactic merger events, where the gravitational chaos of colliding galaxies can reverse stellar orbits and propel stars onto entirely new paths. It is akin to observing automobiles traveling in reverse on a highway, unequivocal evidence of a past catastrophic event. The chemical abundances of stellar populations also reveal periods of heightened star formation triggered by galactic interactions. When two galaxies collide, their gas reserves are compressed and agitated, triggering massive bursts of stellar births. These starburst events create populations of stars with increased abundances of alpha elements such as oxygen and magnesium, forged in the cores of massive stars that lived and died rapidly during the chaotic merger. Different regions of the galaxy showcase distinct stellar populations, each contributing to the larger narrative. The galactic bulge contains older, more metal-poor stars formed during the galaxy's earliest epochs. The disk populations show a gradient of chemical enrichment, with stars nearer the center generally containing more heavy elements than those in the outer regions. The spiral arms themselves generate temporary stellar populations with characteristic ages and compositions. Stars born within the arms carry the chemical signatures of the compressed gas from which they formed, including heightened abundances of elements produced by recent supernova explosions. As these stars age and drift from their birthplaces, they disperse these chemical traces throughout the galaxy. The most metal-rich stars in the galaxy are found in the youngest stellar populations, born from gas enriched by billions of years of stellar evolution. These stars contain the complete periodic table of elements, forged in successive generations of stellar cores and disseminated by supernovae. By studying the ages, motions, and chemical compositions of millions of stars, astronomers can reconstruct the galaxy's merger history. Computer simulations suggest that the Triangulum Galaxy has undergone at least several major merger events, each adding new stellar populations and disrupting the galaxy's structure. The ongoing collision with the Andromeda Galaxy, still billions of years in the future, will add another chapter to this stellar archaeological record. When future astronomers study the merged galaxy's stellar populations, they will find evidence of our present era preserved in the chemical signatures and orbital patterns of the stars we observe today. But these stellar storytellers are only one facet of a larger cosmic cycle, where gravity continuously sculpts new worlds from the raw materials of space. Vast, colossal gas clouds, arms outstretched, yield to the unrelenting tug of their own gravity. In a celestial choreography of destruction and creation, gigantic molecular clouds, possessing enough material to forge millions of stars, drift through space, a delicate equilibrium between expansion and contraction. For millions of years, these clouds maintain stability. Their internal pressure, stemming from random molecular movements, perfectly counterbalances gravity's inward pull. Yet this balance is precarious, akin to a boulder perched on a precipice, awaiting the slightest disturbance to unleash catastrophic change. This trigger frequently originates beyond the cloud's boundaries. A shock wave from a nearby supernova explosion, the gravitational sway of a passing star, or compression resulting from spiral arm dynamics, can disrupt this equilibrium. Once gravity gains dominance, collapse becomes unavoidable. Guided by the same physical laws that shaped our solar system 4.5 billion years ago, the collapse commences slowly, almost imperceptibly. The cloud contracts by a mere few percent over thousands of years, gradually increasing its density while cooling towards absolute zero. However, as the cloud's density grows, its gravitational pull intensifies, accelerating the inward rush of material. What began as a gentle drift transforms into a headlong plunge towards the center. As the gas compresses, it fragments into smaller clumps, each destined to become a stellar nursery. The largest fragments might contain hundreds of times the mass of our Sun, while the smallest may possess just enough material to form a single star. This fragmentation process is chaotic and unpredictable, governed by turbulence, magnetic fields, and the random motions of the gas itself. The collapsing fragments heat up as gravitational potential energy converts to thermal energy, mirroring the warming of a bicycle pump during air compression. Temperatures, initially near absolute zero, climb to hundreds, then thousands of degrees. The gas starts to glow faintly in infrared light, signifying the birth of what astronomers term protostars. But gravity's work is far from complete. As the protostar continues to contract, its core temperature rises towards the 10 million degrees necessary to ignite nuclear fusion. The journey from cold molecular cloud to blazing star takes approximately 50 million years for a Sun-like star, but can occur far more rapidly for more massive objects. The most massive protostars can ignite fusion in under 1 million years, their formation a cosmic sprint. The collapse is neither uniform nor smooth. Magnetic fields weaving through the gas can impede the infall, while rotation causes the material to flatten into a disk encircling the burgeoning protostar. This disk becomes the birthplace of planetary systems, where dust grains coalesce to form pebbles, then boulders, then planets. The same gravitational collapse that creates stars also sets the stage for the formation of worlds. Some collapsing clouds generate not single stars, but entire stellar systems. Multiple fragmentations can produce binary and triple star systems, where two or more stars orbit their shared center of mass. In the densest regions, dozens or even hundreds of stars can form concurrently, creating the open clusters that speckle the galaxy's spiral arms. The process of gravitational collapse operates on numerous scales throughout the galaxy. Individual stars form from the collapse of small gas clumps, but entire galaxies were born from the gravitational collapse of even larger structures in the early universe. The same fundamental physics governs the formation of planetary systems, star clusters, and the cosmic web of dark matter that underpins the universe. Computer simulations reveal that gravitational collapse is a hierarchical process, with smaller structures forming initially and then assembling into larger ones. This bottom-up construction explains the rich diversity of astronomical objects, from asteroids to galaxy clusters, all shaped by this same fundamental force. The ongoing collapse of gas clouds within the Triangulum Galaxy continues to add new stars to the cosmic inventory, at a rate approximating one solar mass annually. This persistent star formation will ultimately exhaust the galaxy's gas reserves, concluding the era of stellar nativity billions of years hence. However, not all collapses are gentle events, governed solely by gravity. When stellar violence intervenes, the consequences can initiate cascades of creation across expansive regions of space. Throughout the Triangulum Galaxy, the cataclysmic demise of massive stars is triggering avalanches of stellar birth in a cosmic cycle where destruction facilitates creation. When a massive star explodes as a supernova, its disappearance is not a mere flash of light. The explosion generates a shockwave that traverses space at velocities exceeding 10,000 kilometers per second, conveying energy equivalent to our sun's total lifetime output, compressed into mere seconds. This expanding shell of superheated gas acts as a cosmic bulldozer, reshaping the galaxy's structure and sowing the seeds for the next generation of stars. This shockwave's journey commences with the star's core collapse and subsequent rebound, propelling a pressure pulse through the stellar envelope. Within hours, this wave escapes the dying star and collides with the surrounding interstellar medium. The collision produces temperatures exceeding 100 million degrees Celsius, sufficiently hot to ionize atoms, creating a plasma so energetic that it radiates in X-rays. As the shockwave expands, it encounters the giant molecular clouds meandering through the galaxy's spiral arms. These clouds, which have maintained stable equilibrium for millions of years, suddenly face assault from a wall of superheated gas moving faster than a speeding projectile. The delicate balance between gravity and pressure maintaining their stability is instantly shattered. The shockwave does not destroy these clouds, but compresses them like a cosmic fist squeezing a sponge. This compression increases the cloud's density by factors of 10 or more, intensifying gravity's influence and initiating the gravitational collapse that leads to star formation. Regions that might have remained stable for millions more years abruptly begin their transformation into stellar nurseries. This process, termed triggered star formation, can generate spectacular bursts of stellar birth across vast galactic regions. A single supernova can affect star formation across areas spanning hundreds of light years, potentially triggering the birth of thousands of new stars. These nascent stars will shine for millions or billions of years, carrying on the legacy of the star whose demise enabled their creation. These shockwaves not only compress existing clouds, but also gather material from the diffuse interstellar medium, acting like cosmic snowplows. This collected material can form new molecular clouds in previously void regions, expanding the galaxy's star-forming capacity and spreading stellar birth into previously barren areas. The heavy elements dispersed by the supernova explosion also enrich the triggered star formation. The shockwave carries carbon, oxygen, silicon, and iron forged within the dying star's core, intermixing these elements with the hydrogen and helium of the molecular clouds. The resulting new stars will exhibit higher abundances of heavy elements than their predecessors, enabling the formation of rocky planets and potentially supporting the chemistry conducive to life. Sequential star formation can create chains of stellar birth across the galaxy. When the first generation of triggered stars includes massive ones, they too will ultimately explode as supernovas, creating new shock waves that can trigger even more star formation. This creates a propagating wave of stellar birth capable of traversing entire spiral arms over tens of millions of years. This process is strikingly evident in the galaxy's star-forming regions, where we observe multiple generations of stars at various evolutionary stages. Young, hot blue stars mark the locations of recent shock-triggered star formation, while older red stars indicate the sites of previous episodes. The spatial distribution of these stellar populations reveals the history of supernova-driven star formation across the region. Some of the galaxy's most spectacular stellar nurseries owe their existence to this process. The massive star-forming complexes that dominate the spiral arms often exhibit evidence of triggered formation, with expanding bubbles of hot gas encircling groups of young massive stars. These regions will eventually produce their own supernovas, perpetuating the cycle of death and birth that has characterized the galaxy's history. The efficacy of triggered star formation hinges on the properties of the molecular clouds and the intensity of the triggering shockwave. Dense, massive clouds are more readily triggered than diffuse ones, while stronger shocks can overcome the resistance of more stable clouds. This creates a complex interplay between stellar death and birth that influences the galaxy's overall star formation rate. The Triangulum Galaxy's star formation capacity, however, is not limitless. Concealed beyond its visible stellar disk resides a vast reservoir of material, the key to the galaxy's ultimate destiny. Past the furthest discernible stars stretches a colossal dark matter empire, extending 10 times farther than light can travel, forming a cosmic structure exceeding the limits of human perception. The vibrant spiral arms and luminous star-forming regions that dominate our view constitute merely the luminous core of a far more extensive gravitational system. Encircling this visible disk is a roughly spherical halo of dark matter, possessing 5 times the mass of all visible stars combined. Were this invisible structure visible, the galaxy would appear as a diffuse sphere, not the elegant spiral we observe. This dark matter halo extends to distances of nearly 1 million light-years from the galactic center, making the true galaxy 15 times larger in diameter than its visible manifestation. The halo's outer boundary is so distant from the galactic center that light from the galaxy's core requires 1 million years to traverse it, a span exceeding human existence. The halo's gravitational influence shapes all within it. The beautiful spiral structure we witness exists solely because the dark matter halo provides the necessary gravitational scaffolding. Without this unseen foundation, the galaxy's rotation would have long ago wound up the spiral arms, destroying the elegant pattern we see today. Computer simulations reveal that the dark matter halo possesses a complex internal structure, featuring sub-halos and density variations reflecting the galaxy's violent formative history. These substructures are gravitational fossils of smaller dark matter clumps that merge to build the galaxy, each contributing mass to the growing halo over billions of years. The halo also encompasses more than just dark matter. Scattered throughout this immense volume are ancient globular clusters, stellar streams from disrupted dwarf galaxies, and a diffuse population of halo stars following highly elliptical orbits. These objects act as tracers of the halo's gravitational field, revealing its three-dimensional structure through their movements. Hot gas, with temperatures exceeding 1 million degrees, fills portions of the halo, creating a tenuous atmosphere around the galaxy. This gas is so hot and diffuse that it is invisible to optical telescopes, but detectable through its X-ray emission. This hot halo may contain as much mass as all the stars in the galaxy, representing a significant reservoir of baryonic matter hidden in the galaxy's outskirts. The boundary between the galaxy's halo and intergalactic space is not defined by a sharp line, but rather a gradual transition, fading slowly into the cosmic web of dark matter connecting all galaxies. This transition region, termed the galaxy's virial radius, marks the approximate limit of the galaxy's gravitational influence and defines the edge of its dark matter halo. Within this vast halo, smaller satellite galaxies orbit like planets around a star. These dwarf companions are embedded in their own dark matter sub-halos, creating a hierarchical structure where halos exist within larger halos. The orbital motions of these satellites provide crucial data about the total mass and distribution of dark matter within the halo. The halo's rotation is significantly slower than that of the visible disk, resulting in the luminous galaxy spinning within its dark matter envelope like a wheel within a wheel. This differential rotation might explain some of the galaxy's observed properties, including the persistence of its spiral structure over cosmic time. Recent observations have detected streams of hydrogen gas extending far into the halo, potentially representing remnants of gas accretion events that contributed to the galaxy's construction. These gas streams might be visible traces of the cosmic web filaments that channel matter from intergalactic space into the galaxy's gravitational well. The dark matter halo also functions as a protective shield, safeguarding the galaxy from the harsh intergalactic environment. Its gravitational field can deflect or capture intergalactic gas clouds, preventing them from disrupting the galaxy's internal structure. This protective role may be vital for maintaining the galaxy's star-forming ability over cosmic time. The study of galactic halos has revealed that visible galaxies are merely the bright cores of much larger dark matter structures. This discovery has fundamentally reshaped our understanding of galaxy formation and evolution, suggesting that the universe's visible components represent only a small fraction of its total gravitational architecture. This protective halo, however, cannot fully shield the Triangulum Galaxy from the gravitational sway of its considerably larger neighbor. Andromeda's tidal forces are already subtly reshaping Triangulum's destiny. Invisible forces are slowly dismantling the Triangulum Galaxy. Its outer regions are stretched and warped by the gravitational influence of its massive neighbor, the Andromeda Galaxy. Tidal forces, the same phenomenon that generates Earth's ocean tides, operate on galactic scales with devastating consequences. The side of Triangulum nearest Andromeda experiences a stronger gravitational pull than its farther side, creating a differential force that stretches the galaxy like cosmic taffy. This gentle yet relentless stretching has been ongoing for billions of years, gradually altering the galaxy's structure. The effects are most pronounced in the galaxy's outer regions, where the gravitational hold is weakest. Streams of stars and gas are being drawn from the galaxy's edges, forming tidal tails that extend far into intergalactic space. These stellar streams trace Triangulum's orbit around Andromeda, like breadcrumbs left by a cosmic wanderer. Computer simulations indicate that Triangulum has lost a significant portion of its initial mass through tidal stripping. Stars once belonging to the galaxy now drift between galaxies, gravitationally unbound, destined for an eternity in the cosmic void. This ongoing mass loss progressively diminishes the galaxy's size and modifies its internal dynamics. The tidal forces do not uniformly impact all parts of the galaxy. The central regions, where stars are more tightly bound by the galaxy's gravity, remain relatively intact. However, the outer spiral arms clearly show distortion, with asymmetries and warping reflecting the external gravitational influence. The galaxy's once perfect spiral structure is being gradually unwound by these external forces. The Triangulum-Andromeda interaction is not a simple two-body problem. It involves the complex gravitational interplay of three major galaxies. Our Milky Way also exerts significant gravitational influence, creating a three-way tug-of-war that complicates predictions of the system's evolution. The competing gravitational fields generate resonances and instabilities capable of dramatically altering orbital trajectories. Recent observations have revealed a bridge of hydrogen gas connecting Triangulum to Andromeda, evidence of direct material transfer between the two galaxies. This gaseous umbilical cord represents matter stripped from Triangulum and captured by its larger neighbor, a slow-motion cosmic cannibalism that will eventually completely consume the smaller galaxy. The tidal interaction also impacts star formation within Triangulum. The compression and stretching of gas clouds by tidal forces can trigger new stellar births in some regions, while suppressing them in others. This creates a complex pattern of star formation varying across the galaxy, with some spiral arms showing increased activity while others appear depleted. The galaxy's dark matter halo is also being stripped by tidal forces, although this invisible mass loss is more difficult to directly detect. Computer models suggest Triangulum may have lost half or more of its original dark matter halo to tidal stripping, fundamentally altering its gravitational structure and internal dynamics. As Triangulum orbits Andromeda, it experiences varying tidal forces depending on its distance from the larger galaxy. At the closest point of its elliptical orbit, the tidal forces intensify, accelerating the stripping process and potentially triggering bursts of star formation. During more distant phases, the galaxy can partially recover, reforming some of its disrupted structure. The tidal interaction is gradually circularizing Triangulum's orbit, causing it to spiral inward towards an eventual merger with Andromeda. This process will accelerate as the galaxy loses mass and orbital energy to tidal friction, leading to an increasingly rapid decay of its orbit. The galaxy is essentially falling towards its demise. Although this process will require billions of years, the study of tidal interactions has revealed that galaxy evolution is not an isolated process, but involves complex gravitational relationships between neighboring systems. The local group of galaxies represents a gravitationally bound system where tidal forces play crucial roles in shaping the evolution of its member galaxies. These external influences add another layer of complexity to the already intricate story of galactic evolution, but they pale in comparison to the mysterious internal rhythms that govern the galaxy's stellar birth and death cycle. Deep within the cosmic machinery of the Triangulum Galaxy, a rhythm pulses, a rhythm astronomers are only beginning to decipher. A cycle of stellar birth and death unfolds, following enigmatic patterns spanning millions of years. Star formation within this galaxy is not a constant process. Instead, it fluctuates dramatically over time. Imagine a cosmic heartbeat, accelerating and decelerating under the direction of some unseen conductor. During periods of peak activity, the galaxy generates new stars at rates 10 times greater than its average, filling its spiral arms with brilliant blue giants and glowing nebulae. Conversely, during quieter phases, star formation nearly ceases, leaving behind only the fading embers of previous stellar generations. These cycles operate concurrently on multiple timescales. Short-term variations occur over millions of years, possibly triggered by the galaxy's transit through spiral arms or interactions with gas clouds. Longer cycles extend across hundreds of millions of years, potentially linked to the galaxy's orbital movement around Andromeda or encounters with other members of the local group. The precise triggers for these star formation cycles remain largely unknown. One possibility is that spiral density waves generate periodic compressions of the interstellar medium, squeezing gas clouds until they collapse to form stars. As the galaxy rotates, various regions traverse these compression zones, resulting in waves of star formation that sweep across the galactic disk like a cosmic wildfire. Another potential driver is the galaxy's interaction with the cosmic web of dark matter and gas pervading the universe. As the galaxy moves through this large-scale structure, it might encounter filaments of gas, triggering bursts of star formation as they fall into the galactic disk. These cosmic rain showers could potentially explain some of the observed variations in star formation rates. The galaxy's magnetic field may also play a crucial role in regulating star formation cycles. Magnetic fields can support gas clouds against gravitational collapse, preventing star formation until the field is weakened by turbulence or reconnection events. The build-up and release of magnetic pressure could create oscillating patterns of star formation throughout the galaxy. Internal feedback mechanisms introduce another layer of complexity. Massive stars, formed during periods of intense star formation, produce powerful stellar winds and eventually explode as supernova, heating the surrounding gas and potentially hindering further star formation. This negative feedback can create boom and bust cycles, where periods of intense activity are followed by relative quiescence. The chemical evolution of the galaxy also influences these cycles. As successive generations of stars enrich the interstellar medium with heavier elements, they alter the gas's cooling properties and the efficiency of star formation. Regions with higher metallicity may form stars more readily, while metal-poor regions may require stronger triggers to initiate collapse. Changes in galactic climate may drive some of the longest star formation cycles. The galaxy's overall temperature and pressure can vary over cosmic time, influenced by factors such as the cosmic background radiation, the density of the local group, and the galaxy's interaction history. These alterations can modify the conditions for star formation across the entire galaxy. Recent observations have shown that star formation in Triangulum correlates with activity in nearby galaxies, suggesting that environmental factors operating on scales far larger than individual galaxies may influence stellar birth rates. The local group as a whole may experience coordinated cycles of star formation driven by external influences. A study of star formation histories in different galactic regions reveals that these cycles are not uniform. They vary spatially. The inner regions display different patterns than the outer disk, and some spiral arms appear more active than others. This spatial variation suggests that multiple mechanisms may be at work simultaneously. Understanding these star formation cycles is essential for predicting the galaxy's future evolution. The The current star formation rate determines the longevity of the galaxy's gas reservoirs and when star formation will ultimately cease. These cycles also influence the galaxy's chemical evolution and the formation of planetary systems that could potentially support life.